Hello everyone, I'm Dr. V. Divya. I'm from Department of Mathematics and today we are going to see the concepts of stress, strain and equation of continuity. In this video, we are going to see the basic concepts of stress, strain and the nature of stress and strain and the relation between the nature of stress and strain, and finally we will see the equation of continuity. So what do you mean by stress? So when an external force acts on a body, it undergoes deformation and at the same time the body resists deformation. So the magnitude of the resisting force is equal to the applied force. This internal resistance per unit area is called stress. So we can express the stress as mathematically as force per area. That is, stress can be denoted by the symbol sigma, which is nothing but F by A, and its unit is expressed in terms of Newton per meter square. And what do you mean by strain? So when a body is subjected to an external force, there is some changes in the dimension of the body. That dimensions can be measured mathematically as the strain. That is, it is given by change in length divided by the original length, which is nothing but delta L, where L is the length, and divided by theta. That is original length. This can be seen in our figure. And next, we can see the forces acting on the element are of two types. One is body force or external force. For such kind of example, for such kind of force is gravitational force, and surface force or internal force, it is within the body. It is the potential within the body. So that is we can classify this as the two kinds of forces. And following that, there are two kinds of stress, namely normal stress, that is normal stress and shearing stress. Normal stress can be expressed, it is nothing but the force applied is perpendicular to the surface. When it is shearing stress, it is the force applied is parallel to the surface. So now let us see the nature of stress and strain. So in elasticity, the relation between stress and strain is governed by Hooke's law, where Hooke's law states that the strain within the material is proportional to the stress applied, and which is within the elastic limit. And in a fluid physical law, connecting the stress and strain can be made by the following assumptions. So the stress components can be expressed as linear function of rates of strain components. And second one is that the relation between the stress components and rates of strain components must be invariant to a coordinate transformation consisting of either rotation or a mirror reflection of axis. Suppose if you are taking an axis, then xy, then if we transform the coordinates to x dash y dash, similar transformation, then it will be reflecting that either it is a rotation or a mirror reflection of the axis. The stress components must reduce to a hydrostatic pressure where the gradients of velocity are zero. And so that based on the above nature, we have obtained the relation between the shearing stress and strain in three-dimensional flows are given by these equations. Since we have 9 stress components, so due to the similarities, we have only 6 components. Instead, that is sigma xx, sigma yy and sigma zz, and sigma xy and sigma yx are equal, and sigma yz and sigma zy are equal, and sigma zx and sigma xz are equal, where here mu is the dynamic viscosity and b is the constant and p is the hydrostatic pressure here. And finally, then we will derive the equation of continuity. So how do we derive the equation of continuity? This equation of continuity serves as the basic equation for the entire fluid dynamics, and it is derived based on the law of conservation of mass. It states that mass can neither be created nor be destroyed. So that first, let us consider a moving surface A enclosed a mass of fluid within tau lying entirely in the fluid. If rho d tau is an element of mass, consider an element of mass, that is rho del tau. So mass can be represented as density into its volume, so that rho into del tau represents the volume, that is element of mass. And then the expression of the law of conservation of mass can be written as, that is rate of change with there is no change is mass, that is with respect to time, so that we can express mathematically as d by dt of rho del tau, which is equal to 0. Then we can write the equation in the above another form as d rho by dt divided by rho plus d del tau divided by dt divided by del tau, which is equal to 0. If we consider the total mass of the fluid enclosed in the closed surface, then equation 1 becomes limit del tau tends to 0 summation of 1 by rho into d rho by dt del tau plus d of del tau by dt, which is equal to 0. The first term in this equation, that is equation number 3, can be rewritten in the integral form as triple integral over the domain 1 by rho into dou rho by dou t plus q dot del rho into del tau. And the second term in 3 can be represents the rate of change of volume, which is equivalent to limit del tau tends to 0 summation d by dt of del tau, which is nothing but triple integral over del dot q into d tau. So in the combining the equations 4 and 5, we can find that triple integral 1 by rho into dou rho by d dou t plus del dot rho q into d tau, which is equal to 0. So from which we can obtain the continuity of equation as dou rho by dou t plus del dot rho q equal to 0. Suppose if the following this, equation 7 may be written in a different form as dou rho by dou t plus q dot del rho plus rho del dot q, which is equal to 0. We know that dou by dou t plus q dot del, which is nothing but d by dt. So from this we can club the first two terms as d rho by dou dt plus rho into del dot q, which is equal to 0. In Cartesian coordinates, equation 7 may be written as dou rho by dou t, that is material derivative d by dt can be expressed as dou by dou t plus dou by dou x plus dou by dou y plus dou by dou z, so that we can apply here, and we have obtained the equation 7 in Cartesian coordinates as the equation dou rho by dou t plus dou into rho u by dou x plus dou into dou of rho v divided by dou v plus dou of rho w by dou z, which is equal to 0. For an incompressible fluid, the density is constant, so that we have obtained the continuity equation as del dot q, which is equal to 0. In Cartesian coordinates, we may write that equation as dou u by dou x plus dou v by dou y plus dou w by dou z, which is equal to 0. Following this, we can solve one of the problem, that is consider a two-dimensional incompressible steady flow field with the velocity components in rectangular coordinates given by u of x comma y, which is nothing but k into x square minus y square divided by x square plus y square, and v of x comma y, which is nothing but the velocity components are given, so that we have to find that whether the continuity equation is satisfied, where k is nothing but the arbitrary non-zero constant. So v is given by 2kxy divided by x square plus y square, the whole square. So we have to find out the equation of continuity is satisfied. So for that, what is our equation of continuity? Dou u by dou x plus dou v by dou y is equal to 0. The derivatives of u, x, y and v of x comma y with respect to x and y are respectively are. So where dou u by dou x can be written as k into x square minus y square. So we have obtained finally the expression, and dou v by dou y can be obtained differentiating v with respect to y, we are obtaining the expressions. So from this we can substitute the values of dou u by dou x and dou v by dou y in the continuity equation. So the combining, we are getting that dou u by dou x plus dou v by dou y, which is equal to 0. Hence the equation of continuity is satisfied. So finally, at last we have learned what do you mean by stress and what is mean by strain, and the relation between the stress and strain and its nature. And finally we have derived the equation of continuity, and based on that we have derived one more problem related to that equation of continuity, that we have checked whether the equation of continuity is satisfied. Thank you.